That's a super creepy voice. I love
that's
it.
All right.
Sorry for interrupting our breakout.
Oh my God, it's hilarious. I love it. All right, David, Papers of Seattle, 7-1. Take it away.
Hi, friends. I'm David, and today we are going to talk about things going really, really badly. It's going to be fun. So I love reading academic papers, maybe not a surprise given that I'm here at Papers We Love, but even more than papers, I really love reading incident retrospectives. Not just how you think your system works, like in theory, but how it actually works out in the real world, especially when things get weird. And like finding out what are the differences between your theory about the system and how that system actually works. So this paper is pretty recent, earlier this year, is Metastable Failures in Distributed Systems, and it's a little bit of both of those things that I love. The authors looked at a number of incident retrospectives from big distributed systems, and they described this theoretical framework to help talk about some of the hairiest of these incidents, in which they use this term metastable failures. That I think is pretty unique to them. Other people have other words for it, but I'm going to use metastable failures. As usual for these things, please feel free to interrupt and ask questions or add additional flavor at any time. I'm not at all standing on formality. So first, a bit of very quick background on distributed systems to make sure we're all level set there. Distributed systems are just systems built using more than one computer. There's a couple reasons you might choose to build a distributed system. Masochism, for example. One of the most common is for getting a higher availability. Computers are ultimately physical things, and sooner or later, physical things are going to break down, right? And if you build a mission-critical system using just one computer, and that computer breaks, you're going to have a really bad day. And even worse, a really boring incident retrospective, right? Our one computer broke. That left us with 0 computers. That wasn't enough computers. Oops. Not like a lot of interesting depth to that one. If, on the other hand, you have built your mission-critical system with multiple computers and one of them breaks, that's potentially not so much of a big deal, right? You've got all of the other computers, and at least in theory, the overall system can keep on working. Hooray, distributed systems. So kind of coming into this with the framing of we're doing distributed systems because we want them to continue to be available. And there are other reasons, but we're not going to talk about those. Of course, computers breaking down isn't the only thing that can cause incidents for your distributed system. There might be a bug in the code, for example, or maybe an operator accidentally deleted the production database. Not that I have ever done that. Let's pretend for a moment that those things never happen. Would our distributed system then be perfectly reliable? Probably not, right? So another very common factor in incidents is overload. When you ask a system to do more work than it can physically do with the resources it has, something's eventually going to fail. Maybe your bottleneck is CPU power, and you overload that and you aren't able to send responses to requests before clients time out and they think your system's down. Maybe you run out of disk space and your system can't store any more data, right? You get the idea. You keep adding more and more load onto any given system, eventually it's going to hit a breaking point and you're going to call that a failure. In a normal system overload case, the problem goes away when you remove the source of the overload. We call that initial source of overload the trigger for the incident, like someone's sending you a denial of service attack. It's eating all of the bandwidth and causing actual user traffic to be dropped. So we put a block list in, drop the traffic from the offending IP addresses. That removes the trigger. In a normal incident, right, then load on the network goes back to normal because we're not having that DDoS attack anymore. User traffic starts making it through again, and everything just magically gets better from that point. It's hard or maybe impossible to completely prevent, these kinds of overload incidents, but it's usually relatively straightforward to recover from them. Sometimes, though, that's not what happens. Sometimes, when you remove the trigger, the system stays overloaded, and it doesn't recover. These incidents tend to be really gnarly to resolve, and they take systems down for long periods of time. The authors call this class of incidents, overloads that continue to keep going after the initial trigger is resolved, metastable failures. We'll get into what that actually means in a bit. First, we're gonna have a story time. So the paper gives a couple examples of metastable failures, ranging from frustratingly familiar stuff like storms of retries to deliciously arcane stories about like multi-link aggregation stuff and connection pooling. They're worth a read if you haven't done that already. I love those kinds of just like, oh, weird, I like never even thought that that was a thing that could happen kind of stories. But this is my talk, so instead we're gonna dig into one of my favorite examples of this kind of failure, the big EC2 outage from 2011. Is anyone here old enough to remember this one?
I just started college that year, so.
Cool. I was not. I was working at Amazon at the time. I was not actually involved in this at the time, or knew that it was happening, or probably even knew what AWS was. But this was a problem with EBS, the big distributed system that hosts the virtual disks for EC2. EBS was built to be highly reliable, and it usually is. It's honestly a really legitimate piece of engineering. But during this incident, they had this issue, and customers were impacted for many hours, and in some cases several days, while they worked to get things back up and running again. Everything I'm going to discuss comes from the public retrospective, which is linked here. It's one of my all-time favorites of the genre, definitely worth a read. So the trigger for this incident was a network configuration change that was made that inadvertently routed all traffic for a subset of the EBS servers in one of their clusters. Instead of going through the high bandwidth primary network that they use most of the time, it accidentally all failed over to this secondary network that was lower bandwidth and never really designed to handle that kind of load. Funneling all that traffic onto the backup network pretty quickly overloaded the backup network, made it really hard for those servers to talk to each other, which then, because they're doing consensus-y bullshit, meant that you couldn't do reads or writes from your virtual disks if they were hosted on one of these impacted servers. So far, pretty normal overload failure. The network change was quickly rolled back. Traffic routed back onto the higher capacity primary network, removing the trigger. And instead of everything getting better, this was when shit really hit the fan. So EBS servers use a buddy system. Every block of data is stored on 2 different disks on 2 different servers for reliability. When a server loses its connection to its buddy, at least at the time, it assumes that its buddy has crashed and that it now has the one and only remaining copy of this piece of customer data that it's storing. So it pretty quickly tries to find a new buddy and sends that buddy a copy of the data. This is a process called remirroring. This works really, really well under normal circumstances for the system, right? When an individual server fails, the system quickly and automatically recovers. Behind the scenes, another copy of the data gets made, everything keeps on working. Yay, distributed systems. In this scenario, however, we had a big network outage, effectively, and then when it came back, there were suddenly a whole lot of EBS servers all doing this process of looking for new buddies and trying to make more copies of their data. Maybe you can see from here what went wrong, right? Pretty quickly, all the remaining disk space in the cluster was filled up because we were trying to make a whole bunch of extra copies of data. That left a bunch of servers stuck in a loop, right? Looking around to try to find a new buddy, not finding one, and just in a for loop, continuing to search the entire cluster for a buddy. That searching process placed a whole lot of additional load on the region-wide control plane service for EBS, overloading that and knocking it offline for several hours until they eventually cut network connectivity to the infected cluster and basically just threw it off the map. To get things fully back online, they literally had to truck in more servers from other data centers in the region, add them to the impacted cluster to increase disk space so this remirroring process could finish, and then very slowly bring the cluster back online to avoid overwhelming the control plane service again. Good times. So the paper calls these kinds of incidents metastable failures and gives a couple other examples. So what the heck is a metastable failure? If you, like me, are not in physics, maybe that doesn't make any sense to you. It took me a long time to parse this because I'm used to the more colloquial meaning of meta, a stable containing other stables. It didn't make any sense to me. So it turns out that metastable here is a reference to a concept of that same name from actual science instead of computer science. So we are now going to take a quick detour to learn about carbon atoms. Bet you didn't think this is where we were headed. So in physics, a stable system is a system in its lowest energy configuration. Under most circumstances, the lowest energy configuration for a system of carbon atoms is graphite, the soft grayish stuff that we use in pencils. If you happen to have a bunch of loose carbon atoms, it's really easy to make graphite. You just wait. Carbon atoms bonded together in the hexagon structure of graphite is a lower energy configuration than just a bunch of carbon atoms. So as they cool down, they'll just naturally link up and solidify into graphite. Once the system becomes graphite, it's stable. If you leave it alone, it will just keep being graphite. You can, of course, add a bunch of energy and blast it back into carbon atom soup, but carbon atom soup is not a stable configuration. As the energy you added dissipates, it'll cool back into graphite again. To make this analogy explicit, stable is how we want our computer systems to behave. They might temporarily melt down if there's an overload situation, but when that source of load is removed, we want things to naturally cool back down and go back to normal. So stable graphite and unstable atom soup aren't the only configurations that our system can have, though. Under extremely high pressure, carbon atoms will instead, apparently, arrange themselves into the more compact structure of a diamond. At sea level, this is a higher energy configuration than graphite. So thermodynamically speaking, a diamond is not stable. It would ideally prefer to give off a bit of excess energy and become a lump of graphite. In practice, though, there isn't a direct path from a diamond to graphite, like there was from atom soup to graphite. It can just cool down. A diamond is, I don't understand enough about how the chemical bonds work, but apparently is sitting at the bottom of this local minimum on the energy graph on the other side of this slide. You have to actually add quite a bit of energy to get it kind of up and over that hump to loosen those bonds, at which point then it can fall apart into graphite. Right, it's going to stay a diamond until someone does that. So scientists call a system in one of these stable-ish configurations metastable, meaning above stable. Apparently that's what meta actually means, just above. It's not actually stable since a lower energy configuration of the system is possible, but it can't get into that configuration from where it is on its own. It's stable until it gets a big enough push. So completing the analogy, in a metastable failure, the triggering overload doesn't just overload the otherwise stable system. It pushes that system into a different metastable state that locks some of that energy in somehow and will persist until the system gets a big enough push back in the other direction to get it back to healthy. The details of different metastable failures vary widely. They have different initial triggers, different ongoing impacts that the system experiences, and different paths to eventual resolution. But the paper identifies some common features that all of these metastable failures share and builds that into a framework for helping us to reason about them as a class. So somewhat ironically, metastable failures are often the result of automation, originally put in place to increase system stability. The initial triggering event activates these supposedly friendly robots, which attempt to return the system to normal operation. But in doing so, they place additional load on the already overloaded system. A metastable failure occurs when this load is itself sufficient to keep the system overloaded, even after the initial trigger is dealt with. Because the system is overloaded, the robots keep trying to repair it. The system is overloaded, so they can't repair it. The repair attempt fails, but they keep trying to repair the system, which keeps the system overloaded, which keeps the robots working, and so on and so forth. It's a bad day. In the case of the EBS outage we discussed earlier, the initial trigger, the overloaded network, activated this feature that normally keeps the system stable by automatically dealing with hardware failures. The large-scale activation of this feature is what pushed the system over into a metastable state, where it was continued to be overloaded long after the initial trigger was resolved. And the overload even cascaded beyond that initial cluster to take up the entire region. Another example, the one I like best from the paper, involved this link aggregation scheme in this system at Facebook. So the system in question consisted, unclear, of two clusters of machines. One of them is a cache and one of them is a database. They're connected. They need a lot of bandwidth between them. So they're connected via multiple physical network cables. And in theory, connections between these two systems are going to be randomly assigned to different links. In aggregate, this group of links provides more than enough bandwidth for the system needs. But each one doesn't need to have many of them. If, however, in this situation, one of those links became overloaded due to a temporary spike in load, maybe it just got unlucky, that system, the whole system, would go metastable. More and more traffic would end up getting routed onto that one slow link, overloading it even further. And then more traffic would be routed to it, and so on and so forth. In this case, it wasn't actually an active repair attempt adding system load, but it's a very similar idea. An optimization that worked well in the normal case, they're doing some connection pooling here, provides the sustaining effect. Rather than opening a new connection across the network for every request between these two systems, they keep a pool of existing connections and they reuse them for future requests. And it turns out during a temporary load spike on one of these links, response times for connections over that link get higher because the link is overloaded. And the way their connection pooling logic worked, that meant those connections were more likely to be selected for future requests. So you end up with the connection pool stacked with connections that are going across that slower link, which funnels more traffic across the slower link, which keeps those connections at the top of the pool. And this effect continues to sustain until basically you turn the thing off and then turn it back on again. So fully abstracted, their failure model looks like this. They put this at the top of the paper. I have explained it backwards. The system that we're talking about here begins in a stable configuration. Everything is happy. We've got enough spare capacity to recover from any problems that come up. While we're in this state, the system might be temporarily overloaded by a big spike in load. Right, our system doesn't have infinite resources, but the system is stable. When that load spike goes away, the system is going to have enough spare capacity above and beyond its normal workload to be able to do its recovery and get back to normal. Over time, as we run the system, the buffer of spare capacity gets reduced, either because we have increasing day-to-day load on the system and we're not scaling up to match it, or because some SVP looks at our budget and says, hey, why do you have this much spare capacity? Why don't you scale down to reduce costs? At some point, we cross this threshold where we no longer actually have enough buffer left to bounce back from a really big problem. The system at this point still has plenty of capacity for its steady state workload, so nothing is immediately going wrong at this point. It's very likely no one even notices the state transition. But the system is now no longer in this stable state. It's moved to this vulnerable state. In the vulnerable state, if a big enough triggering event occurs, the system won't be able to recover from it because it doesn't have enough spare capacity, and it will move to metastable. It'll be stuck in this degraded state. The additional load of doing the recovery provides a sustaining effect, keeping the system overloaded even after the original cause of the incident is resolved. In order for the system to actually recover and get back to stability, we're going to need a pretty significant manual intervention here. So this framework helps us identify some important characteristics of this class of failures and some potential courses of action to mitigate their impact. First, minor soapbox. Efficiency and stability are natural enemies. To be stable, a system needs to have this buffer of capacity reserved for dealing with emergencies. When times are good, this buffer looks an awful lot like waste. It's just sitting there not doing anything productive. It looks like the opposite of efficiency. Reducing the size of the system's buffer makes it more efficient, but correspondingly reduces stability because it puts us at risk of these big events. This certainly isn't a new idea or even one that's unique to systems of computers. It shows up in all complex systems, from ecology to economics. But I think it puts a really nice framing on sort of the core dilemma here. Right? It's not necessarily wrong in any sort of moral sense to run a system in this vulnerable configuration in order to increase efficiency. In a lot of high-scale scenarios, it's quite the opposite. Right? It would be wildly expensive for EBS to always have enough empty disks just sitting around not storing any data, such that if this really big trigger happens and they suddenly need to rear mirror the whole world, that they would have enough spare disk capacity lying around for that. That trade-off probably isn't worth it for them, given how often an event of that size happens. But it's worth keeping an eye on, right? The smaller your buffer, the more vulnerable you are to something pushing your system over the edge. A somewhat counterintuitive approach that I've heard here that I actually really like is the idea of constant work, which I think it's certainly a term I've heard from crypto in the cryptography sense world, but also kind of applies in this systems world. Basically, you can keep yourself honest about your buffer of capacity by just always acting like there's a failure, even if there's not. If there's not a failure, you do the extra work anyways, and then just throw it away if you don't need it. This is pretty inefficient, sure, but it means that when there is a failure, you can be very, very sure that you have the capacity to handle it. because handling it is just the way the system always works. And if it used to work, then it'll probably still work. So next up, the model helps us see that systems become metastable thanks to this idea of a self-sustaining feedback loop. The system is overloaded, which causes failures. The system responds to these failures by changing behavior in some way, potentially even just as small as logging an error message. That puts more load on the system. If this puts enough load on the system, then the feedback loop can become self-sustaining and we have a metastable failure. So if we can identify these potential feedback loops ahead of time, we can try to limit their impact on the system. There's many approaches to this, as there are potential feedback loops, which is to say infinite, but they all basically amount to bounding the amount of work that the system does during a failure. So the circuit breaker pattern is a great example here, and one that is becoming more common, I think. Right, if you're making a call to a downstream service and that call times out, in most normal cases, it makes sense to give it a retry, right? It was probably just some temporary little blip in the network, and if you retry, it'll be fine. Right, but if that call timed out because the downstream service is overloaded and you do a retry, that's adding more load to the already overloaded system, potentially leading to metastability. So a circuit breaker is a client-side shim that notices, oh, hey, like the last 10 times I called this service, it timed out. Maybe I should give it a little break and not send it any more traffic, throttle the amount of load that I'm putting on it to give it a chance to recover and break that potential cycle. Of course, just dampen all your feedback loops is much easier said than done, especially in complex systems where feedback loops like this aren't so much designed as they are discovered. But it gives us a lot of interesting stuff to think about when we're building systems. Bringing things full circle on this one, the Phasalia paper, which was published last year to describe kind of a newer iteration of the EBS control plane, has some cool stuff in there about how they explicitly designed it with some pretty hard upper bounds on the amount of load that the system will accept in this sort of reconfiguration case, where a bunch of the services all need to do this remirroring at the same time, as a direct result of the incident from 2011, which I think is cool. Lastly, so if all else fails and we do end up with our system in this metastable state, how can we recover from it? The model tells us we really only have two options. We can reduce load on the system until the point that it has enough capacity to make progress on recovery, or we can add more capacity to the system having the same effect. Adding capacity certainly sounds like a really attractive option, especially if you're running on an infrastructure that supports stuff like autoscaling. But you have to be really careful with this one, right? Because adding more capacity can sometimes increase load on the system in the short term. That newly booted server needs to do stuff like discovering its peers, synchronizing data, and warming up its cache. And that process can turn into its own sustaining feedback loop. New capacity comes up, it's unable to actually fully boot and become useful because the system doesn't have enough capacity to get it there. So the system is overloaded, so it boots more capacity, and you get the same effect. But if you can successfully dampen any of those feedback loops, then this can be a nice way out, just scaling up the system until the point where it has enough capacity. The option of last resort is you basically just have to reduce load on the system until it is no longer overloaded. That might mean temporarily dropping user work to free up more capacity for recovery, just blocking requests at the front door. Or it might mean being very careful about throttling your recovery work so that users can still get stuff done and will just very slowly recover in the background to avoid overwhelming the system. In the extreme, it might mean you just have to unplug everything, wait a little while for the dust to settle, and then slowly start plugging things back in again. Hopefully that's your worst case and you don't see too much of it. That's what I've got to say about metastable failures. So here's a couple other links you might find interesting if this was your jam. The first is a more detailed incident write-up for the failure from Facebook, the one with the link aggregation. It's from Nathan Bronson, who is the lead author on this paper from his time at Facebook. The next two links are from Amazon's Mark Brooker, who's done a lot of work with EBS. The first is a review of this paper, which is how I found it. And there's also an earlier post in there that has a lot of similar ideas. He uses the term bistable instead of metastable. The last one here, I was hoping to talk about this some. This time, I didn't actually have enough time to prepare for it, but I threw the link in anyways, and I'll have to come back and do another one sometime. It's a paper called "Those Found Responsible Have Been Sacked." I came across it last month. It's a really interesting sort of meta incident retrospective. It's from the healthcare field, and it's this researcher looking at like when people do incident retrospectives, there's kind of this established anti-pattern of like you eventually get to a point where you say like, oh well, this human made a mistake and that's what caused the problem, and it's pretty generally accepted that that is a bad idea, that it doesn't actually help you make your system more reliable. But this paper looks at sort of what are some of the reasons that organizations, even though we kind of know this from the research community, why organizations still continue this pattern, that I thought was pretty interesting. That's what I got. Questions, comments, thoughts? Dead silence?
Do you see any evidence of these groups using like actual systems and controls to do the math, or were they just like, let's add capacity until it goes stable again?
I've definitely heard some Amazon folks talk more recently about that, the like PID loop and control systems. I haven't seen it. I didn't see it come up in this paper at all. It was just a like add capacity.
It's almost tempting to call some of the self-driving car guys and be like, okay, self-driving data center.
Yep.
Let's get some systems and controls in here.
Colin McCarthy from Amazon, I know, has done at least a couple talks about PID loops and how they use those.
Wait, what's a PID loop? I don't know what that is.
I'm going to completely butcher this.
Proportional integrator and derivative. The idea is that every time we do an integral, it's a kind of low-pass filter, and anytime you do a derivative, it's a kind of high-pass filter. And when you multiply by a constant number, you can move things in and out. So if you choose your high-pass filter, low-pass filter, and amplifier well, you can move the characteristics of a system. And it's been used a lot.
Overshooting.
Things like line following.
Overloading.
That went over my head.
Yeah, me too.
Sounds like you have to read a paper about it.
Okay, I'll take a second stab at following it. If you have a sensor that's trying to follow a black line, and you know that you're on a white floor, you can be like, hey, every time the sensor turns from black to white, change the direction that I'm steering. And then you'll go for a while, and then it'll change from black to white again, and you go, oh, I drove off the end of the line again. If you do that, you take a sort of zigzag down the line. So your goal is, okay, how can we smooth this out a little bit so I get a little more aligned to the line? So if instead of looking just at, did I change from black to white, or did I change from white to black, if I take the integral of that number over time, I can move more smoothly rather than these highly jerky changes. Does that make more sense?
That definitely makes more sense. Yeah.
Not that cool.
The canonical example they usually give is climate control.
Yeah, a thermostat's a good example.
Yeah.
If I turn up the thermostat, if it's cold, so I turn up the thermostat really high, it gets really hot, so I turn it down really cold. And so now it's too cold, so I turn it up really high, and I just spend my entire time adjusting my system.
Yeah, you just need to apply some Calc 2 to your thermostat controller hand. I like it. David, that was rad. It was really interesting. Like to have a name for that type of failure. You know.
Mm-hmm. Yeah, this is
For
the thing that.
Oh shit.
It's like I feel like anyone who's spent a significant time operating big systems is like, oh yeah, no, that's definitely happened to me. But yeah, it's a cool like, oh, let's put some actual theory around this and why it happens.
You ever run into those without a distributed system? I've seen that with garbage collectors, where it's all running along fine until you get just a little bit too much garbage, and suddenly your JVM has to do GC, and it's throwing out all of the compiled code, and then it has to recompile that code, which takes more memory, which makes it do more GC. And
To be fair, multi-threaded applications are approximately similar distributed systems.
Mm-hmm.
So
it's a good analogy.
Yeah, I guess you could map garbage collection to a recovery of like, oh, I'm overloaded on the memory access, so the robots are going to kick in to recover by reclaiming some memory, but that puts pressure on other areas that then cascade.
Yeah,
I like it.
There's a fun thing in the paper as well though about that specifically, that one of the approaches to handling this problem is like changing the policy, but that requires global information. So if you have a system that's monitoring for overload and you're under overload, that may also overload the overload monitoring system. So it kind of just it cascades all the way down.
Yeah.
Yeah. There's also the like if you're experiencing like if the load is being added to your system by the system that was supposed to help you recover from like an error, right? One thing that you can do, it's a little weird, but you can if you just basically cache everything that's happening, you cache all the data you're not processing and then turn it off and let it recover, you can like slow recover basically.
Oh, that's interesting. Yeah.
Yeah. If you just like say, okay, we put all the data that we're not processing into a buffer zone, and this is as long as it's a normal, like the data you're not able to handle is normal operated data, and you can handle that within a normal time frame, and you have extra space, you can catch up faster. And you're going to be behind for a bit, but you will end up consistent. I know we've done that kind of thing as in data. Basically, when we've had issues with buffers and stuff, you turn off the system, let it recover, turn it back on, and like feed it back at a higher than normal rate to catch up.
Yeah, you're like building up a queue of work.
Yeah.
So you stop, and something has happened. You stop processing, and you just let the queue build up for a while the system recovers, and then you bring it back up. It's got a big queue, but you can just work through it at a steady rate.
Yeah.
Yeah, that makes sense.
And that obviously requires you to have greater processing capacity than the amount of work you have, but you should have that if that's your expected.
You don't always need greater capacity to pull off a trick like that. Sometimes you can do it with greater organization. I've seen systems where they get overloaded, so you start throwing everything into some Kafka queue, and then you say, okay, I'm going to work off one customer at a time because that's going to be much friendlier to my caches, and I can go much faster with one customer, and then the second customer, and then the third customer.
Yeah, because you're slower under normal cases because you're dealing with everything at once.
Right, your latency went through the roof, but by switching from a streaming mode to a batch mode, you can sometimes get your bandwidth to be slightly higher, even if your latency just got terrible.
That's fair.
Yeah. yeah, you get anytime you have a queue, you get definitely a version of this if you are running at that. Like again, that idea of a buffer of capacity, because like, yeah, something's going to happen. You're going to hit the garbage collection cycle or whatever. You're going to fall a little bit behind. And if you are running right at that level where like the amount of capacity you have is just enough to keep up, but then like something pushes you behind a little bit, and now your queue is a little bit longer, and then something pushes you behind a little bit, and then your queue is a little bit longer, and
Yeah.
eventually you run out of space in your queue and things explode real hard.
Yeah, queue theory is not forgiving. If your requests can come in at all faster than you can service them, your queue will go to infinity, no matter how closely you underscaled something.
It's also interesting to hear you talk about stability versus efficiency. I mentioned this comments, but that's at the beginning of COVID. They talked about that was the big problem with the American hospital system. It's very much built around efficiency, where hospitals, where when load increases somewhere, they'll move that load to another hospital, like nearby, basically. So hospitals aren't built to handle like surges. Like they don't have a lot of extra capacity than normal load, but across multiple hospitals we do. And as long as the load isn't increasing everywhere, the system can kind of like absorb it. But when load increased everywhere at once, we started talking about triaging. Basically, like how do we reduce the load on the system, because we're entering a metastable failure, and so we need to reduce load by.
Yep.
And sometimes our philosophies change over time. For decades, the power grid had this attitude of always balance power from farther away and farther away and farther away, so that it's almost impossible to bring it down. And then we had the Northeast blackout, where we took out several states simultaneously. And people were like, maybe we should have systematic localized failure as part of the system, rather than just tying everything together so nothing fails until everything does.
Yeah.
Seems like a good idea for the first 4 decades.
Yeah, as long as you don't have like you said, as long as you don't have an issue, this stuff all works great until you enter a metastable issue, and then it all doesn't work great.
Works really badly. Yep.
Yeah.
The TCP had this also from a while back. The like exponential back off.
Oh, really?
Oh yeah, that was like one of the TCP was like.
Sorry, go ahead.
I was gonna say it's a problem with one of the problems with early versions of internet, satellite internet, was actually exponential back off, because TCP, if you are slow to respond, TCP assumes there's a problem and it starts exponentially backing you off. And because satellite internet has like a 3-second RTT, you just start exponentially backing off all the time.
Yeah, your window size ends up being 1 byte at a time.
Oh.
Because you don't conform to standards. Sorry,
I was just dealing with an exponential back off problem today. We have a queuing system that is going to be hitting a big load this weekend, and I found out that we're not implementing any back off at all, or any retry for that matter. I'm like, oh no, we're not doing any retries at all. It's going to be bad.
I mean, if you're not doing any retries, you have really great back off.
the best back off you can have.
You can't enter metastable failure if you don't have any recovery systems. You just can't enter that kind of failure space.
It's the silver lining.
Touche.
I mean, you can get people to back off at the user level. When I used to try to register for classes in school, I would this thing that's like, yes, it's spinning. Please don't refresh the page. You're just going to make the registration system even sadder.
Oh my God, I remember those things. Yeah, like, don't click the submit button twice. Love it. Dire warnings on the internet.
You may not have retries, but if your users are motivated, you have retries.
Yeah. Which, yeah, then that definitely stacks in a like, great, well, this system has 3 retries. So like that's a bound on it. But then like the system that's calling it has 3 retries.
Oh yeah, the classic retry the retry.
Mm-hmm.
Mm-hmm.
That's what I like about the circuit breakers is that gives you some protection of like, yeah, you think you've bounded the number of retries, but like maybe not actually. So nice to have something in the data to be like, this looks bad. Let's.
I'm gonna stop the recording now. So
Cool.
goodbye, internet people. Not you guys. You guys didn't say.